So what makes hydrogen so attractive? I've compared two vehicles. One is the battery EV on the left hand side. The other is fuel cell EV from the Nikola company. Hydrogen is the lightest element and has the highest energy density. So you can see hydrogen has clearly one advantage, that is power per unit weight, making it suitable for heavy duty vehicles like trucks and commercial vehicles. It has longer range compared to battery electric vehicles. So if the typical battery EV for the same weight can go for 300 to 500 miles, the same fuel cell EV can go 500 to 700 miles. So there is clearly advantage there. That's why the hydrogen is extremely attractive. However, the picture is not completely so rosy. So you can see there is a comparison of a battery vehicle on the top and the hydrogen car on the bottom side. So when you look at the overall efficiency, that is producing the energy using some green source, to transportation and storage, to taking it to battery, and then the power motor and transmission, the overall efficiency comes about 76% for a battery. But if you take the same hydrogen car, starting with some green energy source, then doing the electrolysis and creating hydrogen, compressing it, storing it, transporting it, and then generating power using fuel cell, the efficiency reduces to around 30%. So there is a huge difference in the overall efficiency rate when you compare battery to fuel cell. And that's the major challenge that we have. So it has currently a very low efficiency due to high energy losses. The second thing that is challenging is that it is very highly flammable, hydrogen gas. Currently, the infrastructure is not present. So for example, in Germany, we have only 60 hydrogen filling stations. And expectedly, we have very high cost because there is no proper infrastructure in place. So that makes fuel cell extremely expensive. Um, and this is the engineering challenge that simulation can help to overcome. So for example, simulation can improve the design, optimize the design, and improve the efficiency. It can help in improving the safety, and it can help in reducing the cost of fuel cell vehicle. So that's why simulation has to play a very important role when it comes to accelerating the fuel cell vehicle development. So this is a typical V&V diagram for design of any system. So you start with requirements and specification. So this is whole concept phase where you design the subsystem and the full system for a vehicle, and then go to the detailed design and optimization of each individual component that consists of the whole system. Once you do the whole component design, you want to do whether my design component is working fine. So you do subsystem integration and verification, and then you go to full system validation and verification to check whether it's working as per the requirements that I set out earlier. In this webinar, we'll be focusing on the right-hand side part of this V diagrams, that is the detailed design, then component integration and verification, and system level validation and verification, and how ANSYS tools can help at each of this step. So whether it is CFD, whether it's structure, whether it is creating the reduced order models, whether it is verification and validation. So we'll first look at component level design, mainly first from the CFD point of view, and then Dinesh will talk about the structural design. So when you talk about the CFD modeling, what it does basically is it couples the overall design of cells and stacks and fuel cell systems, so overall engineering design, with the study of fundamental physical and electrochemical processes that happen inside the fuel cell. So here is an example of a fuel cell where you have this anode channel, you have cathode channel, where your fuel and oxidizer respectively come, and they react at the catalyst and produce electricity. So these fundamental processes are modeled inside when you talk about the CFD modeling, and that modeling will help you design the cells and stacks when it comes to full vehicle development. So what are your design objectives when you talk about the CFD modeling? So you want to look at bipolar plate design, whether your channels will be single serpentine or triple serpentine or interdigitated. You want to look at how my species are distributed. I want to have as uniform distribution for species, current, and temperature as possible, so that my fuel cell is going to operate at highest efficiency. Water management is extremely challenging when it comes to PMFC because it operates at low pressure. So that is something that you want to optimize. Then there are different processes like osmotic drag and back diffusion. Then you want to look at how the different operating condition have an impact on the overall fuel cell operation, like anode humidity, cathode humidity, flow directions, temperature, and then you want to look at the overall stack design as well. So all these design objectives can be met when you do the CFD modeling of fuel cell. So in ANSYS Fluent, what we do, we couple the flow simulation, that is the chemical species transport, the momentum transport, the energy transport, with the ANSYS Fluent fuel cell module, which gives the nonce voltage, over potentials, current density, and electric potential. So these two models are coupled. No, they are coupled through species and heat flux transferred from the fuel cell to the flow simulation, and the flow simulation then gives back to the FC module the species concentration and temperature. Then we'll look at some use cases, how the PMFC can help in not just validating, but understanding what are the different processes that are happening inside fuel cell. So so this is a case from this paper, Mensch and others. So you have this serpentine channel with 50 centimeter square MEA area. The total mesh count was around 400K. And we simulated this particular fuel cell at different operating conditions, looked at different post processing, and we'll look at how the insights that CFD can give to improve the design. So first, this is the comparison of the polarization curve, the potential versus current. Again, we simulated it for different equivalence ratio on the cathode side. 1.5 and 2.25. So we can see clearly at lower equivalence ratio, the curve falls off at a lower current density. But at a higher equivalence ratio, it slightly continues longer to give larger current without consuming completely the reactants. But you can see the comparison is excellent with the experimental data, which are shown by these symbols. Similarly, we looked at current density at different cross sections. Again, the comparison is excellent for different voltage levels. But the most important point that I want to highlight is here. So this is the contour of current density on the plane of membrane. So you can see close to the inlet, you have a very high current density, of course, because of the availability of the reactants. But as the reactants are consumed, as you come towards the outlet, you see that the current density have become lower. Now, you may want to improve this and want to have more uniform current density distribution across the cross section from inlet to outlet. And those kind of insights can be obtained from such CFD simulations. Then we can not only look at a single cell simulation, but you can also look at stack simulations. So this is another use case of stack simulation. So we have 33 channels in a single cell, and 10 such cells are arranged in a stack to provide more voltage. So these are some of the details of the mesh and the CPUs. So ANSYS Fluent is a highly parallel solver, so it scales quite well. And this particular 16 million mesh model was solved on 96 CPUs and solved in 2 hours. The important point I want to highlight here when it comes to stack simulation. So if you look at this bottom corner, so we have plotted temperature contours at different planes, different at a cross section and for different cells. So you can see because this is naturally cooled, so you have cooling at the ends, so you have lower temperature there. But in the middle cells, it kind of heats up because not enough cooling is available here. So we did not have any coolants. It was naturally cooled in this particular example. And this is something that any design engineer would want to avoid this situation, because higher temperature is going to affect your other parameters like hydrogen concentration. So you can see there is a variation of hydrogen concentration across the cells. There is also variation in the relative humidity. There is a variation in the current density. So a design engineer will get such kind of insights from these simulations, and you can also design a cooling system that will avoid such situations. So this was about the detailed CFD modeling, and then we will go to the system validation and verification, how we can achieve that in using the ANSYS tools. So we'll look more into the behavioral modeling of fuel cell. So we looked at the CFD side. So we start with the mesh. We solve it in ANSYS Fluent using CFD. We get such data like polarization curve. The next step would be to use this physics-based model, 3D CFD model, use that intelligence and put that into a system level simulation. And for that, you want to create a reduced order model. So what I mean by reduced order model is basically a relationship, functional relationship between some output variables that you want to test. It could be maximum temperature, it could be maximum relative humidity, some operating condition parameter that you want to look into or control with all the input variables, like inflow, the pressure on the anode side, or maybe the surrounding temperature, or the relative humidity at the inlet. So those are your controlling parameters, and you want to look at the output. So so we want to create that using our physics-based model. And then once you create this reduced order model, or functional mock-up unit, as it is called sometimes, you can put that into a fuel cell subsystem model. So this subsystem model has different components, like it has anode side circuit, hydrogen tank, then there is a cathode side circuit where there is a compressor, there is a humidifier, there is a condenser, there is a cooling circuit here, and so on. So this particular intelligent data is going into my fuel cell subsystem model for a system level simulation. And once you do that subsystem level verification, you can integrate this subsystem model of fuel cell into a full vehicle model, which is shown here, which has other components like battery, it has a car, and traction motor, and so on. So this is for a full vehicle model. But the important thing is that you are using a very high fidelity reduced order model that is coming from your actual design. So how do you do that? How do you create the ROM? So we have a tool called ANSYS OptiSlang, which can allow you to do a design optimization, not only design optimization, but you can create a design of experiments. So you can create different samples and for different input parameters. So here we have selected 4 different input parameters, like inflow of hydrogen, inflow of oxygen, voltage stack, and the relative humidity on the cathode side. And these are several output parameters that you want to look at when it comes to system level simulation. It could be total current, it could be temperature, relative humidity, it could be outflow, oxygen content, average temperature, and so on. So, you can create a design of experiment. So here we had 30 design points, and create a table, dependence table, for example. So how the output parameters are dependent on the input parameters that I provided. So for example, the current is completely dependent, almost completely dependent on the voltage. But there are some variables like inlet pressure on the anode side that is dependent not only on voltage but also on the relative humidity at the inlet, and also the inflow value. So this kind of dependence matrix you can create, and then that is basically your ROM. Reduced order model. So that is the functional relationship between the input and output parameters that you can export for a system level simulation. So this is the FMU that I'm talking about, with inputs and output parameters. Not only that, you can also look at things like safe envelope. So here is a volume chart where the temperature, the maximum temperature of a fuel cell is dependent on three different input parameters: cathode flow rate, stack voltage, and inlet water mass fraction. So in this particular example, if suppose I don't want my fuel cell to operate at a temperature that is greater than 340 Kelvin. So this is basically my boundary surface. So I don't want my fuel cell to operate in the region where the temperature would exceed this 340, that is safe operating limit. So I don't want stack voltage, for example, go below 8 volts. So this is basically a 10 cell stack. So for each cell, it should not be less than 0.8 volts, for example. So these kind of studies can be done, and you can devise control strategies. So for example, if my voltage is going below 0.8 volts, what should be my control operation, or what should be my strategy so that it comes back in the safe operation limit? So these kind of studies can be done using the design of experiment models. Another important point, so we first looked at point ROMs, so where there was one input or multiple inputs and an output, which was a single number. But you can also look at a 3D ROM, or a field ROM. So that can be created using ANSYS Twin Builder. So the advantage of a 3D ROM is basically that you don't really have to do expensive CFD simulation again and again. So you do only simulations for 30 points, and you can basically get the 3D field data at any other point that for which you have not done the simulation. And such field reduced order models or 3D reduced order models can be built using ANSYS Twin Builder. Here is an example of mass fraction of hydrogen at a cross-sectional plane. The top one is CFD result, and the bottom one is the ROM results. You can see that it's fairly accurate when it comes to 3D ROM. So it's almost as good as CFD results. But constructed using only 30 design points. Similarly, these are the CFD and ROM results for oxygen. If you look at the error, in the H2 ROM, we only have a error of 5.5%. In O2 ROM, it's 6.7%. But the great advantage is that you really don't have to run these simulations and again, and without that, even look at the 3D field. Again, this is another example of a 3D ROM where we looked at relative humidity in the fuel cell and static temperature. Again, we see a very close comparison between the CFD and ROM results. So in the relative humidity ROM, the error was 9.1%. In the temperature ROM, it was about 0.2 Kelvin. So that's how close the two results are. Then we can So this was all about ROMs. So how do we use these ROMs? So we can use these ROMs in a system level simulation. We can devise control strategies. We can ensure the safe operation of fuel cell. So this is the ROM that we extracted from our physics-based model in a CFD, and that has been used in a system level simulation, which I showed earlier. So you have this anode side circuit, you have this cathode side circuit. We have just put it in a block here. And this is how a fuel cell subsystem circuit can be created and simulated. Once you do the simulation, so here are some of the results. We ramp up the current for a stack from 100 amperes to 150 amperes and look at how the different output variables behave once we ramp up the current. So here is how the relative humidity is changing, maximum relative humidity is changing in the stack. Then here is how the hydrogen flow rate is changing at the outlet. So you have a fixed inlet flow rate, but as the current is ramped up, you have decrease in the outlet flow rate for hydrogen, and similarly for the oxygen side. So these are the system level. Even you can simulate a drive cycle. So here it was just simpler ramping up from 100 amps to 150 amps. You can do similar studies for even a drive cycle for a fuel cell vehicle. So to summarize, I think we looked at component level design. We looked at how the CFD can give you the insights in the component level design. And the same CFD or the intelligent model that we built can be converted into a reduced order model for a system level simulation in a fuel cell subsystem. And the same can be taken up then in a full vehicle model where you integrate all the parts like battery, traction motors, power electronics, and so on for an electric vehicle. So that's the summary. I then hand it over to Dinesh for the structural design part.
Thanks, Saurabh. I will share my screen. Okay, hope my screen can be seen. Sure. So let's thanks, Saurabh, and let's talk about the structural design. From the structural design integrity aspects, there are a lot of requirements for the fuel cell, just like we have a lot of requirements for even the IC engine and any other kind of the structures that we have. So we have tried to bucketize them into the three major buckets from the structural integrity requirement point of view. So one is like, the assembly process requirements in which the engineers are very much interested to determine what is the optimum bolt load. They want to perform the trade-off studies between the conflicting parameters like contact resistance, GDL porosity, sealing compression, component stresses, strains, etc. Want to ensure the uniformity of the contact pressure between the cells, how the end plate design can affect, the assembly parameters, number of the bolts, how should they be placed, also the gasket, like what should be the optimum thickness and which material is good for the application that is being designed, or number of the cells and their impact, and also like just like sort of showed the developing the reduced order model so that you don't need to run the simulations again and again to establish the relationships between like the compression load, contact resistance, porosity, and again also more detailed simulations to estimate the material properties of the complex materials like MEA assembly, and then do a detailed simulation and so on. So these things can be captured using the implicit solvers, multi-physics capabilities, and tools like OptiSlang. Then the second bucket is fatigue durability and dynamics. So where engineers are interested in determining the natural frequencies of the system to make sure that the natural modes they don't align with that of the excitation modes. The fatigue when it is subjected to tension, torsion, and bending kind of the loads, thermal fatigue because when you switch off and switch on, the temperature rises and goes down, so it is subjected with the thermal cycling, fracture characteristics to make sure the design is damage tolerant. Since the structural parts are immersed into the fluid, so they some parts may soak the fluid and then swell. So how the stresses can be developed, and how the material degradation can happen, the random vibrations which can be coming from the vehicle, how that can impact the design, and thermal and creep relaxations over a period of time, that how much the ceilings would be preserved and so on. So we have capabilities to do this using linear and nonlinear dynamic solvers, smart fracture tool for damage tolerance, ENCODE for fatigue, complex material simulations, including viscoelasticity, plasticity, and so on. And the third bucket is like crash, shock, and fabrication aspects, where engineers are interested in evaluating the structural integrity when it is subjected to velocity shocks, sudden accelerations, thermal shocks, block test, crash kind of simulations. So just like Saurabh stated, that it's very highly inflammable, and in case of accidents, the hydrogen tank should not burst. So is it placed optimally inside the car? Some of the fabrication things like complex parts like bipolar plates. So we can use explicit solvers like LS-DYNA to do these kind of the simulations. So it is apparent that when you go from left to right, the modeling complexities and challenges would increase, and it needs more intense experience CA engineers to perform these tasks. But if you come on the left-hand side, the simulation requirements, the would reduce, but actually the design requirements are high, and more repeatedly the left-hand side things are done more. But it doesn't mean that right-hand side things are not done. It's just that left-hand side things are like the initial things and more repetitively being done. So that's why in this presentation, since it's a very broad topic and we have limited time, so I have plan to capture only some of the things of the fuel cell structural modeling aspects, specifically from the assembly process point of view, but most of them, they also being applicable to the other requirements as well. And we will consider mainly like how do we evaluate contact pressure, like end plate, how the end plates can have the effect, and how the bolt load gets distributed for the over the bolts for the uniform compression and so on. So let's see the typical structural modeling aspects for the fuel cell. So fuel cell will, it can have a single cell or it can have multiple cells.
Dinesh, we are not able to hear you, Mr. Dinesh. Mr. Dinesh, we are not able to hear you.
Just a second. Maybe there is some issue from the network. So I'm checking with him. Just give me a minute.
No, Dinesh is not there. Not able to hear what he's talking about.
So you should have capability to assemble them, and also should be able to apply the displacement of force controlled loading and see the behavior. So even in the assembly process, it seems easy, but it has a lot of conflicting things. It's like the clamping force. Take example of clamping forces. If you increase the clamping force, it increases the stresses and deformation, which may not be good, but it reduces the contact resistance and propensity of the leakage. But at the same time, it may
Mr.
reduce.
Dinesh, we are not able to hear you, Mr. Dinesh. I think
Hello,
you'll have to log in again.
Yeah, I can hear Dinesh now.
can you hear me?
Yes, I can hear.
Mr. Saurabh, can you just inform Mr. Dinesh? There seems to be some problem at his end.
Okay, I can hear him actually.
Uh, okay.
Yeah, I think the voice is clear. I think I can see the chat. Yeah.
Okay,
Go
maybe.
ahead. Go ahead. Go ahead. Yeah, Dinesh.
Okay.
Yeah.
So, so we have to manage the conflicting requirements in the assembly loading given. So we have created one demonstration for a 40 stack model to demonstrate the fuel cell modeling in the assembly loading. And the important components that we have considered here is like end plate assembly, bipolar plates with flow channels, MEA, which is modeled as a homogeneous material, gaskets, the bolts. But some of the things, it is not necessary to take their actual, the geometry. You can take their effects using the boundary conditions, which comes under the idealization steps that helps to reduce the model size. Also, so the demonstration purpose is like to show seamlessly the workflow in the ANSYS workbench, which is a framework to kind of connect multiple ANSYS products, um, and then solver capability. And definitely, if you're interested to learn more, we can help you. We use this as a training material in the details. So in this slide, it shows a typical workflow in the ANSYS workbench, which is like a framework to join multiple systems and products and tools in the ANSYS. So you can see that here, instead of doing the modeling for the whole fuel cell stack, I will just take a single cell and then I will create the mesh contacts and everything for that. And on other hand side, I will have, let's say, the mesh contacts and properties for the other components like end plate. And then finally I assemble here. These are the just few clicks that you will need to do. And since here, let's say I have 40 stacks, so this plus additional 39, which I can create the copies of the whole model, not just the mesh, but also the contact and everything, material assignment and everything. And then I can place them with an offset which is equal to the thickness of the whole single cell. And then I can take them and do the detailed modeling, like applying the overall loading and boundary condition and do the simulation. So let's look at the more closer view of the single cell. So for single cell, we considered MEA assembly as homogeneous material, bipolar plates, gasket, flow channels, so that this can pose challenges for the meshing, but the ANSYS meshing techniques handles it very well. Gasket slots and the thickness that we have considered, the gasket opening we have considered at this point of time for this demo is like around 0.25 mm between the bipolar plates and between the gasket and MEA. So for the meshing, for the bipolar plate, we have done the tetrahedral mesh because this has complex serpentine, the flow channels. And then for the MEA assembly, we have done the hex meshing, and we need to take care of the good quality mesh at the areas where we are mainly interested, like knowing the stresses, like these kind of corners, and also the gasket to place at least two elements across the thickness so that we don't come up with convergence challenges, as well as we capture the stiffness of the gasket very well. You've taken material property from an international journal paper, and for assembly process, they are assumed as linearly elastic. However, we can take care of more complex material properties. The gasket here, you can see that the Poisson's ratio is very near to 0.5, which means that it is nearly incompressible and it's very soft as compared to the other materials. So since there are many parts, we can use the capabilities like automatic generations of the connections between the parts, where the tool automatically identifies the nearest surfaces within the tolerances and defines things like contacts and other connections. And for modeling and smooth solution of when you have very soft parts like gasket, we need to do some specific contact settings which handles the soft materials very nicely. Then once we go into the ANSYS mechanical from the workbench, then you can see the actual model details, where you can see that from every cell they are very nicely segregated into the trees, every cell. And then you have like the contacts from every cell. You can view, you can change if you want to make any change. And then also we can again use the automatic contact creation capability to define the contacts between the cells. So these are the contacts for a particular cell. So a cell can have multiple parts like gasket, and bipolar plates, you need to define the contact, and then between the cells also it gets automatically created. So then the whole modeling time for at least for this model is like from 2 to 3 hours because of this automation, thanks to the automation that has made it easy. Otherwise, picking up the surfaces and defining the contacts and then picking up every part and going to define material property, that will be very difficult. So the instancing and all those things, they help, and the computer does most of the job. So that makes the life easy. Then from the boundary condition perspective, the fuel cells, like we can, during the assembly, we can, fix the end plates in plane directions. And for the bolt, we can apply the displacements from both of the directions. How much displacement we should apply, that depends upon the gaps that we have uh, between the bipolar plate and gaskets. So here in this case, the total gap was around 30 mm. So we apply 15 mm of displacement from both the sides. So this thing is going to close, just close the gaps, and we need to apply additional preload to generate a sufficient contact pressure between the cells so that we avoid the leakage of the fluid. So that's why additional 10% of the bolt load is applied into the second load stat. The model solved smoothly. We used around 192 cores. It solves around in 4 hours, and it captures the physics nicely. It compresses, and you can see it, the load displacement behavior of this fuel cell stack. It's highly nonlinear, and we need very sophisticated solvers to capture this phenomena. So during the gasket compression, the nonlinearity is still moderate, and you need less force just to create, since the gasket is soft. But then once the parts, they come into the contact, like two bipolar plates and bipolar plate and MEA, when they come into the contact, you need to apply additional force. So even for small displacement, you need to apply huge force to generate the contact pressure. So this behavior is captured nicely. And then in order to achieve the uniform compression, so because we applied the same displacement at all the bolts, let's evaluate the bolt preload. So it suggests that the corner bolts would have slightly less preload as compared to the bolts at the middle. And that is because of, when we compress the cell stack, it may cause the bending, okay? And because of that, we may need to apply the additional force at the middle bolts to prevent the bending and uh, to compress it uniformly. Then we can view the stresses and strains. So it shows that because of the compression, most of the MEAs, most of the area, it goes into compression, but still there are areas. Look at these kind of areas. Look at these kind of areas where the geometry is being changed by the gasket. There is a geometric discontinuity, and it causes the tensile stress. And we need to be watchful to this kind of areas. Then contact status. So in the initial load step, when we just close the gaskets, the contacts may be open. The yellow area means the contacts are open. The red area means the contacts are closed. In the second load step, you can see that they are closed very nicely. And we need to make sure that there are no yellow spots specifically in these areas to make sure that there is no fluid leakage. Then we can see the contact pressure contours to make sure that contact pressure is uniform. So there is a slight non-uniformity in contact pressure near the ends, but still at most of the area it is uniform both on the MEA and bipolar plate side. This kind of the charts can be easily produced, where you can, in one shot, you can just see that how actually the contact pressure distribution across all the 40 cells. So it is like the average contact pressure, which is same at all the cells, versus the maximum value of the contact pressure, because contact pressure is varying across the surface. So if you see the end, fuel cells where the contact pressure, the maximum value is high and average value is a bit less, it means that the contact pressure may be non-uniform for these cells. But as you go towards middle, it is more and more uniform, where the average pressure and the maximum pressure are not that much different. So that kind of plots can help us to understand that how the contact pressure would be distributed across the cell stack. This slide shows that the effect of end plate, why the end plate is needed. So we remove the end plate and ran the same simulation. And you can see that even if we apply a good amount of preload, there is a bending, which gets prevented by the end plate. And if you remove the end plate, it allows the bending of the cell stack. And the problem with that is that it can remain or keep the contacts at the middle areas open, and there will not be any contact pressure. That is the reason that we need an end plate. But when you employ the end plate, you need to make sure that end plate weight is not too much, but at the same time, the stiffness is sufficient. So we need to have enough amount of rigidity for the end plates to achieve the uniform compression across the cells, as well as to make sure that there is no, areas where the contacts are open and there is no propensity of the leakage. So this is all from my side. So since the time is limited, but we have a lot of literature, available, which suggests the use of which like uses ANSYS to do a lot of detailed calculations like producing ROMs, optimization, contact resistance calculation, experimental validations, fracture calculations, damage tolerant design calculations, and crash simulations, and some of the fabrication aspects. And even for this demo, we have taken one more step, which I will not be able to show in today's presentation, is like doing a, a dynamic analysis to predict the natural frequencies. So that's all from my side as well. And thanks for your time, for patiently listening to this presentation.
Thanks, Mr. Dinesh. Thanks, Mr. Dr. Saurabh and Mr. Dinesh. Before we move on to the Q&A session, we'll be having a short poll survey. Now we request the attendees to participate in the poll survey, which will help us to have your feedback and serve you better. Now the poll is live. There are 3 questions. The first 2 will be having radio buttons, and the last one you have a multiple choice option. So you may choose any number of options. So we'll be having 2 minutes for this survey. I request everyone to participate in the survey. The first question is, did you find this webinar presentation helpful in understanding the key challenges and simulation solutions for fuel cell vehicle development? The options are yes, to some extent, and no. The next question would be, would you like ANSYS to contact you to discuss on simulation solution for hydrogen fuel cell development? You may choose yes or no on for this. And the last question, you can select more than one option for this. Which of the following should be the most important focus for you in hydrogen fuel vehicle development? Options are fuel cell stack design, fuel cell embedded control, integration and system validation of fuel cell based EV powertrain, or all of the above. So I request all of you to participate in this poll. Following this poll, we will be having the Q&A session. Mr. Sanjeev, we
Hello.
will unmute you now.
Yes, yes. Hello. Good afternoon. It was really a good presentation by both the two experts. I have one queries about the stack design and the temperature variation. What you have shown in the through uh, like temperature difference from the one point to other point. Now here, at the same time, the current density variation also you are shown in the one end to other end. So when all the stacks are uniformly, you know, supplied by the fuel hydrogen. So yeah, here, yes, exactly. So yeah, when all these stacks are being supplied by the fuel in a constant or the constant flow rate, so how there could be a variation in the temperature happens from one end to other end?
Okay. Okay. So during the basically every stack is a, reactor, right? So hydrogen reacts with oxygen in a way to produce electricity. A
Yeah.
byproduct of that reaction is not just electricity but also heat.
Yes.
So so you have heat generated in every cell of this. But what happened here is that you have this surface is exposed to the atmosphere, which is at lower temperature. So is this surface. So you have more heat transfer from here. So that's why there is a gradient in the fuel cell stack if you go from top to bottom. So here the heat here did not have enough chance to dissipate quickly compared to here. So this one is at a lower temperature because it is exposed to atmosphere, and this one is not. And once you have this temperature gradient, the temperature is in turn going to affect the electrochemical reactions, and that's why you have different consumption rates for hydrogen and oxygen across the stack. So that's how the variation actually takes place.
Yeah, you mean to say because of the ambient temperature, there is a effect of the external,
Yes,
end plates are being better cooled and the insides are not
correct,
properly cooled.
correct.
Okay. And another thing, what could be the operating temperature of this fuel cell as you
This
have
is
mentioned?
80C. For
80C.
this, yeah, this example, it is 80C.
Okay.
This is PMFC, low temperature PMFC.
Yeah. And how about the stack current? So they are all vertically mounted, right?
They
All
are
stacks
vertically, yes.
vertically mounted. Okay. And another thing, maybe it is a out of this presentation. I just want to understand the same fuel cell if it is used for the electrolyzer purpose or it's a reverse operations. So we can use a fuel cell as a electrolyzer as well as fuel cell depends on the need. So
Correct.
what could be the change of the chemistry if it is used as a electrolyzer? Can it be the same or will it be any modification in the fuel cell?
It's actually, yeah, it is same
Yeah.
as such. Overall operation is just reversed, as you said. But yeah, there are some considerations like water transport and basically water management that needs to be taken care of once you have converted um, uh, the fuel cell into electrolyzer. But yeah, a basic principle of operation is same, just reversed.
Okay. That's fine. The lifetime of the, like I'm a bit worried, curious to know about this. The lifetime of the fuel cell stack can be increased or decreased. It depends on the stack or the layer which is there in between anode and cathode. So once it is used as a fuel cell, then the width of the layer may increase, or if it is used as an electrolyzer, it may decrease. So how does it, going to increase the lifetime by,
Okay.
using a pure hydrogen fuel? Like as per my understanding, if the hydrogen is purity is very high, then the effect of that one is very low on the membrane.
Yeah, so you're right. So if it is a very pure hydrogen, it basically does not have any contaminant that will affect the reactions. So if you have, typically if the hydrogen is produced from natural gas, it will have contaminants like CO, and they will block these porous catalysts. That will reduce the performance. It will cause degradation and also affect the life. Yeah, so those things need to be taken care into when you are designing the fuel cell. Probably I did not explain that here, but yeah, there are some degradation models also. Once when you are simulating fuel cell, there are models also which can be included. I did not cover that here, but yeah, you're right. So the life would depend on how much purity is there for the hydrogen that is used as fuel.
Thanks, Mr. Saurabh. There's another question from Anish. Is asking, are there fuel cell sellers in India? If so, can you suggest one?
I'm not completely aware about any fuel cell manufacturer in India, but there are some. I think there are some academics who. I mean, there is a university in Tamil Nadu. The professor there has developed fuel cell indigenously. But apart from that, I'm not very sure about any manufacturer in India at this point.
Thanks, Dr. Saurabh.
Yeah.
And Dr. Arun Sambat has asked for two things. First thing is, he wants to know whether you have models for balance of plant, and he also wants to know if there are case studies on HFC simulation for ground level and high altitude level. For example, Leh, Ladakh.
Yeah, so for balance of plants, I think it's something that can be explained based on this fuel cell subsystem. So it has different components, right? So it has compressor, it has humidifier, it has condenser, it has a cooling circuit, external cooling circuit. So these components together will constitute a model for a plant, which is used for the balance of plant. So yeah, we have these models in ANSYS Twin Builder, which can be used for balance of plant model.
Thank you, Dr. Saurabh. We have a question from Arnab Ganguly. How was the contact created for multiple cells? Was it through some external macro or ANSYS as an inbuilt macro?
Sorry, is that a question for me or Dinesh?
Yeah, it is for
Okay.
me. So contacts, I think, yeah. So we have an inbuilt function where you can set the tolerance and you can say that okay, within these tolerance, if there falls two surfaces, pick them and create a contact. So it's very helpful. It's already inbuilt. There is no additional macro script we will need to write. Yeah.
Thank you. Now the next question is from Mr. Venkatesh. For uniform distribution of reactants, people started using open cell metal foam. Is there any research work and modeling going on this?
Sorry, can you get back to the question?
For uniform, yeah, I will repeat. For uniform distribution of reactants, people started using open cell metal foam. Is there any research work and modeling going on this?
Um, I'm not completely aware. Again, when we are simulating or creating any model, we would need these properties. So I'm not familiar complete, to be honest, because I'm from the simulation side regarding the material research.
The next question is from Anna's side. Does ANSYS solver take into account water in liquid form in the cathode GDL while stimulating single cell or stack?
Yes. So yeah, we simulate multi-phase flows. So there are three different distinct phases for water that are taken into account here: gas phase, liquid phase, and the dissolved phase in the ionomer.
Thank you. The next question from Charles. How is the fuel plate modeled, and what is the average element size in modeling fuel cell plate?
Yeah, the element size generally should be, since the cell plate is a thin part, so it's modeled with the solid elements, and the element size is generally of the order of thickness. So in general, it's like 2 to 3 times of the thickness in the plane. But at the areas where you have curvature and the thin areas, where there it's like of like 1.5 times or 1 times of its element thickness, depending upon how many details that you want to capture. Yeah.
Thank you. Mr. Surendra has a question. Is ANSYS able to calculate the water generated in reaction, converting to liquid phase, and the heat generated by its phase transformation is included in the temperature distribution?
Yes, so we consider the phase transformation from one gas phase to liquid phase, or also the water generated during reactions, as well as the phase transfer. So we take all into account when we model fuel cell.
Thank you. Purushottama has a question. Bipolar FEA well simulation. Is any capability in ANSYS? Any reference papers?
This is something I have not explored, but I think in general welds, we simulate. Uh, the only thing is for the weld, we need to apply the accurate material model, to take care of its strength. But I'm not done on this model at this point of time. Yeah.
Okay. Thanks a lot. And then we take the last question from Mr. Sujit. If liquid water is modeled, can these predictions used to build boundary conditions for water separators or droplet distribution?
Yes, absolutely. I think liquid water is modeled, and we'll know at what operating condition what is the amount of liquid water that is generated. And as I said, these things can be taken into account when we are devising control strategies like water separator or humidifier and so on. So yeah, definitely we can model that in ANSYS tools.
Thanks a lot, Dr. Saurabh and Mr. Dinesh. That was an interviewing session. I also thank the attendees who have attending the information section. We request you to kindly take some time to mail us the feedback on this session so that we may look up to improve our delivery for the next time. You also can suggest us 2 topics on which you want us to organize the webinar in future also. We also thank the ANSYS team for the sponsoring for this webinar. Looking forward to meet you all soon in our next webinar. Thank you all.
Thank you, everyone.
Thank you.